With our Module 5 lecture, we're going to continue to look at Portland cement concrete. With this lecture, we're going to take a look at mixed designs, trial mixes, high-strength concrete, and mixing, placing, and curing of concrete once we start to put it in place on a job site. The mixed design, concrete are designed for the strengths required on a project, which we've talked about before. It comes from the design professionals' evaluation of the soil conditions and the load bearing capacity that the concrete has to have to hold the structure up. So of course, we want to also take into consideration deterioration due to exposure conditions. Of course, the environment's going to take a toll on concrete or any type of building material, and other causes, and to allow for effective and satisfactory placing of the plastic material. And again, plastic means in the construction world fluid motion of the material. Often the owner or agency specifies the proportions required in a mix. However, in most cases, only the required strength, exposure conditions, and the placing conditions to be met are specified. The mix proportions have to be developed through mixed designs or experience and the specifications of the reference authorities. And again, this is when we're going to hear something about PSI. Is it 3,500? Is it 4,000? Is it 5,000? What is that PSI strength that we're looking for? When we look at our mixed designs, there's many factors that have to be considered in calculating the quantities of the materials to use in the laboratory trial mixes. And again, we're going to hear terms 3,500, 4,000 PSI, 5,000 PSI. So we want to know what kind of strength does our concrete mix have to have in order to support the structure that we are looking for it to hold up over the course of time. Also important are the types of aggregate and the available locality of this. And again, we talked about this. Cost factors come into play. If we can get this aggregate locally, it's going to save us money. Of course, if we can't, then we have to bring it in. So we may do a mixed design based on the locality of the aggregate to see if we can get that strength we need. Highway authorities have well-developed procedures for completing mixed design calculations with various aggregates for, of course, various types of construction. Many other concrete mixes are developed by private consultants or contractors following the requirements of many standard organizations. And we've looked at ASTM, AASHTO, and there's some other ones here that are involved in the development of different concrete mixes. Items that have to be determined according to the requirements of the standards being followed include, we look at the relative density, the specific gravity, and the absorption of the aggregate. Of course, we talked about that before. Dry rotted density of the coarse aggregates, fineness modulus of the fine aggregates, slump for various types of construction, the water cement ratio for various strengths, and various exposure conditions that we have. Over design factors that have to be taken into account to allow for variations in production harshness or finishing potential. We look at the maximum size of the aggregates for placement, air entrainment, requirements for the exposure conditions, the use of SCMs or special admixtures for various construction conditions. And of course, in the PowerPoint presentations, we have some design examples that will illustrate the considerations of these factors, as well as the specifications of various organizations for design mixes that we have. Let's take a look at trial mixes, and must often be produced to establish the best proportions of the cement, the water, the fine and coarse aggregates, and other materials to use to meet the project's requirements in an economical, of course, safe manner that we're looking to do. And again, we take this, we add the aggregate, the water, the cement, and then we build our trial mixes to see if we can get the PSIs that we need for the structural design. Air content, slump, and strength are usually measured using various proportions of materials. The size of the trial mixes vary, of course, but are often 3-strength test cylinders are compared or prepared, and we go from there. Therefore, a mix perhaps a cubic foot might be prepared, and the criteria and design procedures recommended by the American Concrete Institute and the Canadian Portland Cement Association are outlined. When we look at our cement mixes that we are going to do, or design mixes, of course the proportions of cementing materials can also be calculated using the volume occupied by each component. The ACI method discussed within the PowerPoint presentation with the examples, and the amount of fine aggregates required is obtained using the masses of the components. An alternate method uses the absolute volumes of the components. Of course, the method is also included in the CPCA manual. And again, the following examples, we're going to take a look at the PowerPoint presentations that are in this module to show us how to do these calculations. High strength concrete. Since the 1970s, many advances have been made in the concrete industry and technology. And of course, research development helps us do these things. One of the most significant improvements has been in the production of very high strength concrete utilizing supplementary cementing materials and water reducing admixtures. The following table, of course in the PowerPoint presentation, gives a suggested strength classification system for concrete with some possible components and other properties that we could use. High strength concrete mixed with the slower reacting supplementary cementing materials gains a considerable amount of strength after the standard 28-day period that we have. Of course, the specifications often require that the strength or design strength be met at the 56 or 91 day of the age instead of the 28. Materials production and placing of the high strength concrete must be controlled very closely. Coarse aggregates are usually obtained from crushed rock, preferably fine grained, to give the best cement particle bond that we can create. The proportions of particles that are long or thin must be kept to a minimum, and we discussed this in an earlier module lecture. Smaller size aggregates, we're looking at 3/8 or 1/2 inch. Maximum size are generally best as more area is available for the cement bonding. And what we're trying to do here is give that surface area so that we can have these aggregate particles bond together to give us the strength that we need. Fine aggregates should have the amount finer than the number 100 and number 50 sieve limited, and a fineness module is between 2.5 and 3.2 to reduce the water demand that we would have. Natural sand has been found to give better results than material manufactured from rock crushing. Admixtures usually required include water reducing agents or high range water reducers to allow workable cement or concrete at very low water to cement ratios, and retarders to provide additional time for finishing the drier concrete mixes that we have. Let's move on and take a look at the mixing, placing, and curing of a concrete pour. Concrete mixes can be designed to acceptable standards and specifications, but the construction practices also have to be satisfactory to ensure quality structures and pavement. Concrete mixes are prepared a batch at a time at a central plant. Aggregates and cementing materials are weighed into a stationary mixer or directly into a ready mix truck. About 10% of the water is placed in the mixer initially, then most of the balance with the admixtures to add with the aggregates. All the water must be in the mixer before 1/4 of the mixing cycle is completed. Let's take a look at the mixing procedures. There's essentially 3 types of mixing procedures that are followed depending on the type of plant and trucks that are used. We get the central mixed. This is a mixed, or the concrete is mixed in a stationary mixer at the plant and delivered to the site in a truck with a rotating drum, or in a special non-agitating truck. The shrink mix concrete is partially mixed at the plant with mixing completed in the truck. The third method is the truck mix, and the concrete is mixed completely in the truck after it has been loaded at the plant. And one of the key things here is once this concrete is in the drum and it's traveling down a road, there's a time frame there that we have to actually get that out of the drum and have that poured at the site. If we don't, the concrete will start to harden inside the truck and we get what's called a hot load. If that concrete solidifies inside the truck, we're basically in there with a jackhammer trying to get it all out so that we can then use that truck again. Mixing specifications. Specifications for mixing require 70 to 100 revolutions of the drum at a mixing speed of about 6 to 18 RPMs for most trucks, followed by agitating at a lower rate of 2 to 6 RPMs until the concrete is placed. Minimum mixing time is 1 minute for the first cubic yard and 15 seconds for each additional cubic yard, and 1 minute for the first cubic meter with 20 seconds for each additional cubic meter. Discharge must be completed within both 2 hours and 300 revolutions of the drum. And this discharge, again, is what I was saying. If we don't get that done, we get what's called a hot load, and it starts to solidify within the drum, and now we have concerns about it hardening. And of course, as I mentioned, now we're looking to jackhammer all that concrete out of there. Concrete placement. The concrete must be placed in the forms so that no air voids are left and there is no segregation in the mix. Buckets, chutes, pumps, and belt conveyors are used to move the concrete to the forms. It should be deposited as close as possible to its final location and not allowed to fall freely or too great of a distance. In forms, the concrete should be deposited in layers of 8 to 20 inches thick. Vibration is required to consolidate the concrete and fill all the voids. So we'll have vibration machines, jitterbugs, things like that. It allows that aggregate to kind of move around and get that air out of the mix. The vibrator should be inserted in the concrete about every 18 inches along the form and should penetrate the layer below. Over vibration, of course, can cause segregation or reduce the amount of entrained air in the concrete. Joints between pores must be dampened and covered with a layer of mortar to ensure a tight, waterproof joint. Let's take a look at concrete finishing. Finishing concrete slabs involves screening or striking off the concrete to the required grade, edging to form a slightly rounded corner at all joints, floating to remove any surface imperfections, and troweling. The troweling, usually with a power trowel, compacts the surface, interlocking the aggregate particles and the paste into a dense, hard layer. Finishing should not be attempted with any bleed water on the surface. This must be allowed to evaporate or be removed with a squeegee before troweling. Curing. Curing is one of the most important aspects of the concrete construction business. Poor curing and the addition of extra water at the site are probably the two most common factors that contribute to poor quality concrete. Proper curing requires water and a favorable temperature. When concrete is allowed to dry, the process of hydration ceases because water is required to react with the cement. Concrete will gain strength indefinitely, although at a slower rate, if kept moist. If dried, it is difficult to get it resaturated, and even if it is resaturated, the ultimate strength will probably still be less than if it had never dried out. Methods of curing used to ensure that moisture is present include ponding, sprinkling or fogging, wet coverings such as burlap, kept spraying it, waterproof paper, plastic film, curing compounds that form a membrane when sprayed on the surface, steam curing. The duration of the curing period varies according to the type of project and the type of concrete. And of course, we're also looking at environmental conditions. What's the sun? What's the temperature? Where is the sun? Is it cold? How's the wind blowing? There's a lot of factors that come into play there. A period of 7 days is often specified. In critical cases, the degree of maturity of the concrete can be measured, which will be discussed later, and the time required for sufficient curing determined. Curing must be a continuous operation. Alternative periods of wetting and drying could lead to crazing of the surface. Ponding and continuous sprinkling or fogging are fairly expensive methods and are used mainly on smaller projects. We usually see this on driveways, sidewalks, and things along these lines. Wet covering, such as special types of burlap, are effective but must be kept continuously damp by periodic spraying or covering with a polyethylene film. Wet hay Straw, soil, sand, sawdust, any of these can also be used, but may discolor the concrete and are liable to dry out or blow away unless precautions are taken. Waterproof paper consisting of 2 sheets of paper with an asphalt adhesive or plastic sheets is effective in preventing evaporation of the moisture. Coverings must be held on the concrete surface. Curing compounds sprayed on the surface are the most common methods used for curing pavement slabs. A membrane forming compound prevents evaporation if the surface is covered completely with a sufficient quantity of the material. The rate of application of most compounds is basically 120 to 160 square feet per gallon. Application should be uniform and preferably applied with spraying equipment. When hand sprayers are used, a second coat applied at right angles to the first should be considered. Concrete hydration. The hydration of concrete is often accelerated. This shortens the time required for curing and protection, especially important for precast concrete when forms have to be reused each day for efficient operation, and for winter concreting when the cost of protecting concrete from freezing is high. Acceleration methods used include steam curing using high early strength cement and accelerating agents. Steam curing is often used in precast plants. Steam is applied about 4 to 5 hours after pouring. This rises the temperature as well as ensuring that water is present. The steam is usually shut off in time to allow the concrete to cool and be removed within 24 hours of casting. So what we're looking at here is we have to keep in mind that we can't continuously buy forms. So most of the time forms are used, whatever a pour run may be. Those pours are then broken down, forms are moved, and we reuse the forms and move on. And these are ways to accelerate the concrete curing process. When we get into precast plants, again, we have a controlled environment, forms are made or used, and then we pour these forms, and we may be making catch basins. You're constantly making them, so we have to break the form down, reuse it, and then so on. The following figures, of course, look at the PowerPoint presentations for this. Shows the amount of strength gained that is possible using steam. The use of high early strength cements also allows the period of curing to be reduced significantly, often to 3 days or less. This concrete will usually reach over 80% of its design strength in 3 days. Accelerating agents speed up the rate of hydration and, of course, the strength gained. Calcium chloride is often used. The amount should not exceed 2% of the mass of cement, and it cannot be used in reinforcing concrete as it is a corroding agent, as mentioned before. But if we decide to use poly-coated rebar, we can take a look at that, but it's a cost factor that gets into the price of doing the work. Let's take a look at concrete joints. Joints must be used in concrete construction to prevent the concrete from cracking. Improper joint construction is a frequent cause of cracking, and of course, this is a visual defect in a concrete slab or a floor slab. In the pavement, we look at the edges of the cracks soon break off. They fill with debris, the concrete expands, and the material along the edges, again, the cracks, and it fills or fails. Cracks occur due to the volume change of the concrete, which is basically caused by the drying, shrinkage, and the temperature changes that we have. Control joints must be placed in slabs to allow for the drying and the shrinkage effect that's going to take place. In floor slabs, they should be placed at intervals that are not over 30 times the slab's thickness and in both directions, resulting in basically a square shape that we're going to have. Construction joints are usually located at the end of the 1 day's pour or between lanes in pavement slabs. They are designed to allow load transfer with dowels or keyways. Isolation points or joints are designed to separate the slabs from each structure as column bases, catch basins, and walls. They're usually fanned with a pre-molded filler, of course, which is left behind or left in place. The following images, again, you'll see those in the PowerPoint presentations, kind of show us these joints or joint construction. Outside temperatures and curing during hot weather, there's an increased danger of low slump, quicker setting, poor finishing conditions, and variable air content. And I mentioned this before. The sun's hitting that, the water's evaporating faster, it's curing quicker, so we really got to keep an eye on that. Combination of high air temperature, high concrete temperature, low humidity, high wind velocities cause surface cracking. There's a risk of this when the rate of the surface moisture evaporation exceeds 0.1 pounds per square foot per hour. Specification require that concrete be less than 32 degrees Celsius or 90 degrees Fahrenheit when it is placed. CSA requirements are the maximum 35 degrees Celsius for sections up to 0.3 meters thick and 30 degrees Celsius for thicker sections up to a meter thick. Often it appears that the water should be added to the mix at the site. However, this can seriously affect the properties of the concrete. The use of retarding agents or admixtures or ice in place of water in the mix will improve conditions. Spraying with water immediately after placing helps prevent excessive evaporation. Curing procedures should follow finishing as soon as possible. Temperatures below the 5 degrees Celsius or the 41 degrees Fahrenheit slow the rate of hydration substantially, and below that 14 degrees Fahrenheit it ceases for all practical purposes. In addition, if the concrete freezes before much hydration has occurred, stresses in the highly saturated concrete can be disruptive. The ASTM requirement for minimum temperatures of the concrete at placing are 55 degrees Fahrenheit for sections up to 1 foot and 50 degrees Fahrenheit for the sections 1 to 3 feet in thickness. CSA specifications require a minimum of 10 degrees Celsius. If the expected air temperature at the time of placing or within 24 hours is 41 degrees Fahrenheit or less, precautions have to be taken to protect the concrete. This could require enclosures, windbreakers, heaters, insulated forms to prevent freezing until the strength is at least 500 pounds per square inch. Concrete should be heated at the mixing plant, but not to over 59 degrees Fahrenheit by using hot water or hot aggregate. High early strength cement or accelerating admixtures can also be used. This concludes the Module 5 lecture on Portland cement concrete. And again, please make sure we take a look at the PowerPoint presentations that are part of this module to assist us in looking at the examples that will help us with the homework assignments that are required to be submitted.